So I was at the founding meeting that set up Singularity University, but I've actually been following the thought patterns that go into what was called Singularity for a long time, and actually have lived through many eFols of some of the exponentials that Ray and others have used to characterize where we're going. And you're at a very, very interesting moment in time. You know, I was doing my first computing back over 40 years ago. And yet, in the decade ahead of you, virtually all the components of computing and storage and networking are going to exponentially cross through human capability. Now, that doesn't necessarily mean that, you know, a planetary-wide intelligence is going to arise spontaneously and take over the world, because if you look in the physical world, long ago we've had machines that can do things thousands of times faster, like jet planes, or lift giant things compared to what humans can do. So we've had this surpassing of human characteristics before. What's interesting is when it passes through cognitive capabilities, whether or not it'll be different. And I don't know. So what I'm here for today is to simply show you where we are now and going in some of the underlying technologies and relate those back to some of the points that Ray discusses in his book. We're going to look at supercomputers, scalable visualization, and personal light paths, that is internet, that is just dedicated path for you. Each of these is going through a human characteristic. And the reason that things like what Ray has done in the intelligent machines, spiritual machines, and then Singularity, what Ray does is listens to the exponentials. And what exponentials do is make the impossible routine as they just continue on through some threshold. And you go in non-exponential linear space, you see an S-curve going from very early adopters to growth to maturity. This is the automobile adoption, which you can see took 40 years to really go through its phases. And the National Science Foundation tends to invest in this early phase. Cal IT2, our institute, tends to work in this early phase where it's early adoption of things that may or may not change everything. So here I am, a baby picture of me. This was back in 1990 when I was the director of the National Center for Supercomputing Applications, and this is the Cray YMP. It was $15 million. It could do gigaflops, billions of floating point operations per second. And the NSF net backbone, which became later the internet, was megabits. Well, now you go forward 15 years, that same computing power is in a $1,000 or less, by now less, laptop, same computing power, exactly. In fact, your PC probably has more memory than the YMP had. And a megabit to the home is completely normal, right? So this testing things out at the elite frontier of scientific research, and yet them ending up over a decade or so as a mass market, happens over and over and over again, which is one reason that we actually fund science in this country. For instance, the NSF is funding the first sustained NSF supercomputer called the Blue Waters at the University of Illinois. It'll be 1 million times faster than that YMP. And it's partly because of parallelism. Just like the brain has a very different form of parallelism, but that's why it's as powerful as it is. And what this lets you do is to, what computers are much better than humans are at, is to take the partial differential equations that define the laws of physics and solve them in high resolution of space and time. And so you can see back in '87 when we first took the equations governing the atmosphere with the solar radiation coming in and the equation of state of water going between water vapor and ice and so forth, you could get something that looked like a self-excited thunderstorm. Now, with the much faster supercomputers, you're actually able to zoom down in and to see phenomena like vortical cores forming that actually are tornadoes within a very, very large thunderstorm, all of which are being simulated. So if you look at the NSF supercomputer centers where they have teraflops, so 10 to the 12 floating point operations per second. They're being used for all kinds of things, from better fuel cells to bird flu drugs, Alzheimer's, and so forth. So vast a range of scientific applications. Now here I just scanned this out of Ray's book yesterday, and this is going back through this period from 1990 on up of the various computers that are in places like the Department of Energy labs and so forth. The two red dots I added are petaflop, that's 10 to the 15 floating point operations a second, and exaflop, which is 1,000 times that, just like a petaflop is 1,000 times a teraflop. And so you can see that in this period from 2010, where already we have sustained petaflop, until about 220, this next decade is where we're going through the 10 to the 16th, which is right there, which Ray considers a conservative number, I love that, for the computing power of a human brain. Now I'm not going to go into all the ways you can figure out what is a likely number for the computing property of the brain, because he covers that in his book and he has many references. But I just want you to see that you're going to be living through that period. Here is a picture of the first petaflop supercomputer, which was at Los Alamos. And one of the things I found interesting for this group is that one of the applications that they're now able to do is to model the human visual cortex, which is back here, mimicking 1 billion visual neurons and trillions of synapses, and that they think they can now do this in real time for the entire human visual cortex. So when you read Ray talking about these computers being able to simulate, or you see some of the work that I think you've heard before from IBM that's been working on the monkey brain, to me it still seems like science fiction, and yet, I know scientifically that it's actually happening. And in fact, there are lots of drivers for this. Most of the drivers for developing supercomputers are not to figure out the brain. That's a pretty minimal side issue. It's driven by national defense, by energy, controlled energy, by things like astrophysics, medicine. These are the chemistry, these are the big issues that convince Congress to put the money into it. But what I think Ray and Singularity University have focused on is that inadvertently, these are driving us to a point where actually reverse engineering the brain becomes a possibility. Now, where are we going? Well, this is the road to the exaflop. I just went out on the web and grabbed a few headlines. Oak Ridge, the Jaguar supercomputer, will be at 2.7 petaflops by the end of the year. In Japan, NEC and Fujitsu are working on 10 petaflop computers. IBM plans a 20 petaflop. And this is a quote from one of the exaflop studies. I'm on the Advanced Scientific Computing Advisory Committee for the Department of Energy, and they're heading straight toward the exaflop by 2018, 2020. So this freight train isn't about to slow down. Here's another way of looking at it. Every year, there's a group in Tennessee that looks at the fastest supercomputers in the world and ranks on the top 500 list. So I just went there and got their chart. And so these are real machines. This is the #1 fastest. This is the 500th fastest. And, or I guess this is the one, this is #1, this is the sum of all of them. But if you just look at this is the fastest particular computer. You can see it's a little bit stepwise, continuous. And it's going from 100 gigaflops, and up there is 100 petaflops, which is 2015. So unless something goes wrong with the way things have been going, and I don't see any reason for it, that's 10 to the 17, which is 10 times what Ray thinks is necessary to equal the computational capability of the brain. Now, one of the things that you can see that I certainly am convinced of is that this is an engineering approach to building supercomputers as opposed to a biological evolution approach, which is the way we got our brain. one way you can see they're very different is that this thing requires tens of megawatts of power, these supercomputers. Your brain, you as a human, run at about 100 watts. So there's about the engineered computers are about 1 million times hotter, or that is 1 million times less efficient use of energy to do the same computation as your brain. And so I think we're kind of running out of steam on this engineered thing. And my prediction is that over the next 10 years, you're going to see a radical flip toward biological mimicry of designing these computers. And that's why IBM is working as hard as it is on understanding the wiring of, say, monkey brains or human brains. Now, that's a prediction. It's not necessarily going to happen. But another way to look at it, back in the early 2000s, before the crash, I was involved with a company called Entropia, which was putting together massive numbers of PCs, hundreds of thousands of PCs on the web, and voluntarily getting their computing put together, you know, to make a very distributed fabric, like SETI at home, for instance. Well, if you imagine just 10 million computers, there's going to be the number of personal computers in the world by 2020 will probably be a few billion, right? So 1% of that would be 10 million. So let's just say only 1% of the PCs in the world are hooked together by the internet. And say by then their average speed, and that's pretty conservative, would be 10 gigaflops. And their average free storage about 100 gigabytes. That means that this thing will be, just PCs hooked together by the net will be equal to this 100 petaflop that the top engineered supercomputer will have, and 1,000 petabytes of storage. And whether it's Moravec, who quite a few years ago really began to project forward this intelligent robots, or Kurzweil, or Bill Joy, or Werner Vinge, all of these folks are you know, realizing that something interesting may happen as we cross this threshold, whether it's by distributed collection of computing devices or engineering them. And in particular, I don't know if you've looked at Koza's work, this is a number of years ago at Stanford. He just got 1,000, back then it was a big deal to get 1,000 processor Beowulf cluster, just a Linux PC cluster. And he started putting software segments and then allowing them to mutate and then evolve them. And he found out that eventually he could do over 20 tough problems that you're like sorting problems or other kinds of algorithms, that his evolved software, which when you read it didn't make any sense, could beat the best human design software, more efficient. Now that's a little straw in the wind, but I think that's worth digging into because, again, that's an evolutionary approach as opposed to an engineered approach. The other thing is that Ray and Moravec and others talk about mobile robots. You know, the mobile robots have Wi-Fi, so it's not like they have to just have the intelligence on board. They have their open to the whole internet and all those extra supercomputers. So as they begin to design robots that are being fed essentially from the planetary scale computer, that can pretty rapidly change what happens in robotics. So let's now get down from computing to your iBrain system, which is a fantastic evolved system. I just give you, I'll give these slides to you later, so you can look up some of these things. But here are just two articles that talk about trying to figure out how quickly can information go through the iBrain system. Now your iBrain system is not a video camera. It's actually vastly more complex what it's doing. There's a lot of local processing going on in the retina. There's a lot of reconstruction of reality going on. You have, your fovea has very high resolution, whereas your broad retinal field doesn't. And yet your eye is darting all around, sampling at high resolution, and the brain's remembering all that. And so it's a lot more complicated than a video frame. But nonetheless, whether you look at, this is looking at spikes going down the optic nerve, and they conclude 10 megabits a second. Up here, you're getting about 15 million resolution pixels per eye, which puts it about 10 billion triangles per second. That is, if you're rendering computer graphics, if you could do 10 billion, you're essentially exceeding the ability of the human eye-brain system. Here's the way I did it, I don't know, 10 years ago. If you've ever seen, well, you haven't, but if you could see 4K, which is 4 times HD, it's the digital cinema standard. We have this sort of stuff going on in our institute. It essentially looks photoreal. And that's 8 megapixels, so 4,000 by 2,000 as opposed to the 1,000 by a little bit that you've got. Well, let's just call it 10 megapixels, because you're working in the exponent, so it doesn't matter how close you are, you know, in terms of what's in front of the thing. And let's just say, you know, if you had a 1 byte deep of color, that's like 256 colors. Well, you could see more than that. But 3 bytes is like 16 million colors, and you can't see resolve colors better than that. And you could argue, is it 30 frames a second or 60 frames a second? But when you're looking at a movie, you do not see individual frames because your brain is not capable of time resolution more than about that. You multiply those 3 things together, and it's about 10 gigabits a second. Okay? Well, we're just now crossing to the threshold of being able to do 10 gigabit per second networking. Here's, again, I scanned this just from Ray's book, but you can see starting down at 10,000, right now we're up at 10 billion bits per second as the backbone of, say, the Internet 2, which connects 200 research universities. So if you think of all the traffic generated by each of those universities, times 200 of them, it's going over one 10 gigabit channel on a fiber optic as shared internet. Okay. So what we've been working on is, okay, but what if you just gave that 10,000 megabits per second to a single person instead of sharing it with all the people on 200 research universities? And our colleagues have built a global set of these optic pipes that allow you to communicate at 10 gigabits a second, which, as I said, is probably in excess of what the eye-brain system can handle, and to hook up the major innovation centers around the world. Now, we are researching a terabit per second, and in our photonics lab, they're saying by the end of this decade, they'll be at 50 terabits per second, which would be 50,000 times the eye-brain. And there's something called the National Lambda Rail that connects all the various state dark fiber networks and all the universities. So this is all in place. It's not like in the future. So we're looking at California about how do we get all of this. Think of this as an optical overlay for data-intensive science to the normal internet. So the normal internet is for little objects like emails or little web pictures. Those are about a megabyte. Scientists deal with gigabytes, right? I was just over at the Lunar Science Institute looking at their images, right? These are much bigger. And so we're building a kind of a parallel internet just for small teams of scientists to use where you can transfer large amounts of data. And we're linking up now all the universities in California for this. Here's an example of doing that 4K. 4K digital cinema comes out of the camera at about 7.5 gigabits a second. Okay? So it fits in a 10 gig pipe just barely. This is compressed down to about a half a gigabit per second. Now remember, you at home have maybe a megabit. So this is 500 times what you'd have. Now if you're in Silicon Valley, maybe you got 5 megabits, or maybe you've got 10 megabits, but it's not 500. And so we have this directly between Keio University in Japan, which is one of the best private universities in Japan, and Cal IT2. And this is linking up the chancellor of UCSD with the president of Keio. And you can see this is taken in our auditorium. These are people sitting on the stage, and this is the image coming in at 4,000 by 2,000 pixels, okay? And if I ask you, which of those look more real? Which humans look more real? The ones that are virtual from Japan are the ones that are physical in the same camera image, right? Most people would say that the Japanese look more real. The only thing about that is, notice I'm projecting off my PC, which only has a megapixel resolution. when you're sitting in the auditorium and you're seeing 8 megapixels, it's 8 times that real for the Japanese image. So it's essentially photorealistic. So now what you've done is essentially imagine these walls disappearing, and somewhere else in the world there's a room, and its wall disappears, and now those two physical spaces are virtually conjoined into one space, right? And the people are life-size, and you can, you know, share objects in the room and talk to each other. That's what we're doing with this stuff. Okay? So that's part of the transformation that this is leading in the world. And I'll just give you an example that we're only getting started. So they're building a very large distributed radio telescope that either South Africa or Australia or both will have, called the Square Kilometer Array. If you go to the specs, it has to be able to move a terabyte image worldwide every minute. Okay, at 10 gigabits a second, it takes 10 minutes to move a terabyte. So if you're going to do this, you're going to have a lot more than 10 gigabits. And so already commercially, 100 gigabit is available. That's beginning to be deployed, like Department of Energy backbone is being upgraded. But it's going to need even, you know, more than that. So they're looking as forward as they build this instrument, say 5 to 10 years from now, they're following the exponential forward and designing it to be able to fill it with data for the bandwidth we'll have there, which will be far beyond where we are talking about now. Well, then how do you get this, how do you take advantage of this? You know, say you're in a lab and you're connected to the shared internet and you've been doing everything at 10 megabits a second, and I come in and say, no problem, here's an optical fiber. Now you're getting 10,000 megabits a second. You know, it's like if you take a straw and it's good for sucking water out of a glass, but if you open up a fire hydrant and put your mouth in front of it, it doesn't work so well. You have to impedance match, right? And so we've created, there's been this long history I won't go through of creating these very scaled tile walls, which you have one here in the Lunar Science Institute, and you have another one over at the Supercomputer Center. And that allows you to zoom up the number of pixels, and it's connected to a Linux cluster, so you can scale up the computing, scale up the storage, and it's all built out of commodity PC stuff, so it's very cheap. And you can integrate high definition. This is looking at HeLa cancer cells at the UC San Diego. Those are real-time feeds out of the microscope over here. This is remote video back into the control room of the microscope. You get this very weird, you know, interweaving of the physical world and the virtual world. Now let's apply it to, say, a brain. So this is actually a confocal microscope image. It's actually several thousand images of a rat cerebellum. So this is the motor part of the brain back here. It's about, you know, half the size of your little fingernail, really. But it's been sliced and then stained. And the nuclear DNA is the blue. The red is the part of the brain, the glia cells that hold the brain up. And the green, the red is in the green of the Purkinje cells, which we'll see in just a second. Now you'll see how folded the brain is. That's the large-scale structure of it. It means that things here and things here, which are along the brain's surface, very far apart, here are very close together. And I think that's part of the secret of how the brain is organized. Now, if I ask you, okay, here's a slice of the brain. How much magnification do we need to see an individual neuron?
A lot.
A lot? That's what I thought, too. So let's just use the wall to zoom in. Now, already you can begin to see, with just a factor of 2 zoom, I wonder what all these things are along the edge of the walls. Okay? Remember, blue is DNA, and you zoom it in. Those are the Purkinje neurons. And they're all lined up magically by evolution and development. And out here is the famous dendritic overlap that allows the synapses to all talk across multiple neurons, that gives the brain the special computing capabilities it has. So most people, I think, wouldn't expect that at the macroscopic layer of the brain, organization of the brain, that in fact sitting right in front of them are the individual neurons. Now you can see, right? So the brain, the ratio of the individual components of the brain to the brain itself is much closer than you might have thought. And so when Ray talks about reverse engineering, when you look now at this, it doesn't seem so crazy. Not that any of you thought it was crazy. Also comparing brains. So here's one of the projects we did up at Irvine. And so these are a combination of both different people's brains in doing MRI, but also using different MRI instruments, each of which has a signature of the way it does the mathematics, and now being able to compare them across many brains so you can begin to sort out the actual structures. You can figure out where the paths are linking together different parts of the cortex using these white matter bundles. And this is work that when you look at the wall, you actually can rotate this around in 3D. And if you zoom in, you can see that each of these is labeled because we can. Right? So what you're seeing is the large-scale structure and the fine-scale structure at the same time, and that's the great advantage of this kind of thing. You can do it in 3D. This is our cave virtual environment, where you're looking at a RNA polymerase linked to a DNA molecule, and it's all totally surrounded at you in full stereo when you're in there, so you're like in the middle of the molecule. Or it can be used to hook up to remote supercomputers. This is computing cosmology. Now, when you begin to tie the network that we talked about earlier together with the visualization, you could imagine taking these video, either high-definition video or digital cinema, and integrating it with this large-scale visual structure. And that's what we did with Australia. This was the first of these walls in Australia just a little over a year and a half ago. So we're in the auditorium in San Diego, they're in Melbourne, and they're looking at this, and we're just talking to each other as if we're in the same room. And this was such a big deal that the Deputy Prime Minister and the essentially Governor of Victoria, where Melbourne is, were here for the demo. And that has since led to Australia deciding to build the largest infrastructure project in its history, which is to put fiber optic to every one of the buildings and houses in Australia within 80 years, 90% of them anyway. And they're investing, you know, we have a broadband initiative in this country, about $7 billion. Well, on a per capita basis, their program would translate into about $500 billion. And yet we're only spending $7 billion. So other countries are really taking the lead on this. I did a 3-week tour of Australia talking to a lot of their universities, and as a result, the number of these optoportals just mushroomed. And in fact, Australia now has more of these than any other country other than the US, and they're tying them together with each other and worldwide. Here, up at the University of Washington, one of our colleagues is using them to look at the genomes of the ocean diatoms that are the objects, the little macro fauna in the water that produce about every 5th breath you take of oxygen as a waste product. And they're very sensitive to, for instance, acidification of the ocean, which is increasing as the CO2 increases. And we're talking with each other over uncompressed high definition at about 1.5 gigabits a second while she's explaining all this to me. Probably the furthest out one is by Michael Sims, who's here at NASA Ames. That's him there. He programs the rover on Mars, and he normally works in the Jet Propulsion Command Center. And here he's demonstrating that at Cal IQ2 he can sit there, run the software, and talk to his buddies over at high definition, linked to the JPL machine room or control room, and then that's the image coming back from the rover from the software he sent up to execute. So this is essentially an interplanetary scale collaborating, involving robots and humans mixed together. In fact, this is the virtual handshake that between NASA Ames and Cal IT2. This is the person who developed the software that runs all these walls. This is the wall in NASA Ames, and this is taken from NASA Ames, where the high definition coming back from Cal IT2 is on the wall. How much bandwidth can this take? Well, this was a project that is done by the Electronic Visualization Lab. Each of these, this is Chicago, this is Michigan, and this picture is taken in San Diego. This is a 4K digital cinema image, which is streaming. Notice it's replicated on all of the others, and they're seeing the high definition of each other, so it's like they're all in the room looking at these complex objects all together. And it was replicated in supercomputing, and this is the amount of bandwidth on a, this is minute to minute. Here's 10 gigabits and there's 20 gigabits, and the human eye-brain system is down here. Okay? So the thing I find most fascinating about this is that there's this new global platform being created with speeds exceeding both in computing, in connectivity, and in visual resolution, human brains all over the world. So now when those human brains are put together with this enabling technology, it's a little bit different than the worry that the software is, going to take over the world and, make humans into slaves or whatever. That may happen yet, but first of all, what's happening is humans are getting more powerful because they can get their brains working with each other with robotic generators of DNA arrays or interplanetary images, and that is sort of going to lead to the next generation of what Tom Friedman talked about in The World is Flat. He was saying back in 1500 to 1800, nation states like the Netherlands, Spain, England became global powers. And then globalization 2.0 was really when corporations and developed that kind of power you see today. And globalization 3.0, which he said starts in 2000, really empowers individuals to work together on this global scale. Now, the interesting thing is, if you've ever read his book, which you should all have read his book, it's very, very insightful. He's talking about how the shared internet and the web and shared global software has caused this revolution. Well, that stuff's, the internet was in the 70s, right? The web was in the early 90s. This stuff is 1 to 2 decades old. So he's talking about what happens when that kind of stuff has been adopted on a global basis. But what we're talking about is with these dedicated fiber paths streaming HD, the world isn't going to be flat. It's really going to be like reduced to a single point that we're all in. And I think that's as much a part of the transformation that Ray envisions as the artificial intelligence piece is. And something that Singularity University ought to really be considering. So they've asked me to shorten my talk so we can have more time for interaction, so I'll just stop there. And turns out that they wanted me to start at 1:30. So a few of our visitors. Okay, so I'm open for questions. Yeah?
I want to find out more about the bandwidth that you have available. It's just between universities. Is there any media companies or entertainment groups? They would really, media companies and entertainment groups would, I think, be the first to jump on the giant water pipe of information.
Right, exactly right. So the question is this just for universities as 10 gigabit a second, or is the movie industry gotten involved? Well, movies are a 100-year-old analog technology, so that you move stuff around on silver halide film that's been organized into images. All that's switching into a flow of bits globally. So it costs $1 million a day to make a movie. So you can't, it used to be that 8 to 5 was okay, but nowadays it's just not you've got to work 24 hours a day on the bits. So as soon as the bits come out of the camera, they're going off to, say, Singapore or New Zealand, to a special effects house from California. They're being worked on. Then they go to London, where there's all these special effects houses with a fiber network around London. And then they come back around to California. By the time the director comes in the next morning for the digital dailies, all this work has been done, right? But that's being done over either the shared internet or they're FedExing disk drives, which is kind of amazing to believe, but they are. So we realized that there was an opportunity to help them transition as private sector. So we created at Cal IT2 a program called Cinegrid, which is a public-private partnership with all the companies from Lucasfilm to Time Warner to Disney, things like Skywalker Sound, all of the ecology of companies around that, because they don't have a place to go test this out. Amazingly enough, you know, a movie studio doesn't own a global 10 gigabit network it can play with. And we need the application driving from the real world users of it. And so that's why we have set this up. It's worked very well. We have about 200 people every December at Cal IT2 from all these industries and from the universities around the world that work on film, like USC, which you might expect was one of our founding members.
I was wondering if you could talk a little bit about simulations. So you talked about sort of gathering the data and transferring it, but there's that big step in the middle where we have to present it in such a way that it makes sense to us.
Well, so simulation is a word that is, yeah, there's what is called mirror worlds, where you actually use simulation, say, of partial differential equations to create a digital version of some piece of physical reality, like the thunderstorm I showed you. That's appropriate where you have a capability of, you know enough about the underlying laws of physics that you can do that. Then there's visualization, which is taking data that isn't necessarily like the pictures of Mars or something like that, or the molecules you saw. And what you have to do there is develop a visual metaphor, right? Because what you see isn't the real thing. It's a visual simulacra of the real thing. It's a virtual representation in some ad hoc convention. And so when you know, if I went back to the tornado, I happen to be from Illinois, so I know tornadoes, and they don't really look like this. Okay, let's look at this. If you look up in the sky, you don't see stream tubes, but the underlying wind is going along a path. And so if you threw a little dust in, it would trace out over time this path. That's what these little balls are. Okay, and if you actually saw Twister, you know, they actually deployed these instrumented balls into the tornado. Here, they're artificial balls into an artificial tornado. You could argue whether or not this is the way the world would really work. Well, actually, the initial conditions for this severe storm was taken from a real storm in which there were real tornadoes. And it turned out that although it does simulate pretty well the path of the major tornado, some of the this thing actually spawned some little side vortices. Those were not observed. So one reason we want the supercomputers to get faster and faster is because until they get past a certain level of discretion of the phenomenon, you're not going to lock into the way the real physical world works. With visualization, the reason we do visualization is real simple. If you can count up all your neurons in your brain, roughly half of them are involved in visual processing. So humans, evolutionarily, are very visual primates. And you know, you could argue the ones that weren't got eaten by saber-toothed tigers and didn't have children, and the ones that had better visual cortexes escaped and had more children. And so eventually all that's left is people that have better visual cortex. Whatever. The point is that we do have visual cortex. And so if you want to input stuff into the brain where it can use all of these fantastic pattern recognition capabilities the brain has, then the visual way is the way to get it in. Now, that's fine, but if, say, you're looking at financial transactions on a global basis and there's 100 different financial instruments, and so you're following, so you have a 100-dimensional space. How do you visualize a 100-dimensional space, right? Well, completely artificially. You have to invent it. So one of the things we've found is having artists, digital artists, as part of the team. The visual artists are much better at coming up with unconventional visual metaphors than regular scientists. In fact, they're usually the worst. And so this team approach of, say, computer scientist, an application scientist, and a computer artist are really the way to go. And so we pioneered this at Illinois. It's, of course, used on Pixar or any other modern place, because a lot of what goes on in animated movies now is physics-based, and that's why it looks so real. Okay? So you have people who understand bone structures under the dinosaurs, right? And in Jurassic Park, and are part of the team. Yeah.
One of the early case studies about mass screens, say for teleconferencing, was done between university centres where they had free bandwidth, and the most effective screen was the one they put in the coffee room for informal communication. Have you seen with the work you've done any sort of further analysis of that, in the sense that what happens best is actually sort of the discussion between people on an informal basis creates sort of new ideas rather than just virtualizing a traditional technology?
Right. I mean, one of the problems is that traditional commercial video conferencing is all about business meetings. There are 200,000 business meetings in the States daily, right? So that's a market. And so people are trying to replicate what it is with two people sitting across the table talking to each other. Okay? That's not the sort of environment, the informal environment you're talking about. Now, by the way, this goes back a long way. In 1988, or over 20 years ago, I was fortunate enough to happen to be at Bellcore, which is the research arm of the regional Bells. And they had constructed between their two labs, Murray Hill and Homedale, which were 50 miles apart, just an amazing thing. It was like I don't know what it was, a liquid crystal. I'm sure it was the most expensive one on Earth, but it was like 8 feet by 4 feet, and it just looked like a window. And they had actually sort of wide-angle video cameras and all kinds of ad hoc stuff that was pretty, unconventional at the time. And they put them between two coffee rooms. And the experiment was to see whether you would talk to your virtual colleagues on the other side of the wall who were life-size. I mean, this thing looked absolutely real 20 years ago, right? And would you talk to them more than you talked to the people on the physical side? And the experiment was deemed a failure because you kept talking to the people who you actually physically associated with on a daily basis more than these people who you might know who they are, but you don't have this sort of primate, back of the hair on the back of the neck, trust and all that, whatever that stuff is. This is really weird primate stuff, right? Being primates, we pretty much inherited most of what we think is human behavior. And so, of course, they tended to bond more. It was easier emotionally and psychologically to talk to people that are just like you normally run into than ones who are there. Plus, there was a barrier of the virtual. So they took it down. It's crazy, but they did. And Xerox PARC did really great experiments in this. University of Michigan actually probably has the best program in the country in studying how collaboration is used in human teams. We've been talking here at NASA Ames about more research on collaboration for, say, the mission teams, where there's a lot of informal work as well. I mean, it's not like a meeting, it's social network technologies, are fairly new in their takeoff integrating that with this kind of thing, I think, is a real open area of much promise. Yeah. Let's see, was there one back there? Yeah.
How much of the failure do you think was due to the lack of physical proximity versus lack of intimate knowledge of each other? In other words, suppose you had a group of the people who knew each other.
Right.
They had been in physical proximity on an extended period of time, but now they were physically separated.
Well, those are precisely the sorts of psychosocial studies that need to be done more of. There are conferences on this. There's lots of literature full of this stuff. But there hasn't been nearly as much engagement from the research community that would like to use this technology to do, say, scientific research with the social behavioral studies as there should be. It's something I've been urging NASA Ames to take a lead in. Because we, working primate A working with primate B, much less C and D, this is very complex. It's the behavioral interactions and all the zillion little signalings that are going on, right, that they're hard to do over, say, a telephone conference call, and yet they're critical to deep levels of trust. And so, anyway, more and more studies need to be done on that. I don't know, it's not my field, but I do work with people like the University of Michigan, which is one of the best research groups in that area. John Seeley Brown, other people like that I work with.